Hello, my name is Mamia Ijewa Hansen, and I'm going to discuss how we can understand cache memory and memory mapping techniques. Okay, so by the end of this presentation, you will understand why cache memory matters, the main mapping techniques, and how they influence computer performance. Why cache memory matters. So first of all, let's know why cache memory even exists. So cache memory is like a super fast middleman between the CPU and then the main memory, the slow main memory. And then the cache memory stores frequently accessed data, so the CPU does not have to wait too long to fetch data or instructions. This improves overall system speed using the principle of locality of reference, which means if we've used certain data recently, there's a high chance we'll need it again soon. Moving on to what is memory mapping in cache. So memory mapping is a process that decides where each block of the main memory will be stored in the cache. So the key part of maximizing cache efficiency and ensuring data in which is retrieved quickly. So it's a key part in maximizing cache efficiency and ensuring that data is retrieved quickly. So we have three main techniques. We have direct mapping, we have full associative mapping, and we have set associative mapping. So let's dive into direct mapping. So in direct mapping is the simplest approach. So here, each block of main memory is assigned to one specific line in the cache. And we use the formula cache line is equal to block number mod number of cache lines. And it's fast and easy to implement, but the drawback or the disadvantage is conflict misses, which means that if two blocks need the same line, one has to replace the other, even if there are empty lines elsewhere. Now we move on to full associative mapping. And in full associative mapping, it is the most flexible. And here, any block can go into any cache line. It uses something called tag comparison to search the whole cache for the data. So the advantage of this technique is that there's very few conflict misses and a high hit rate. But the disadvantage is that it's expensive to build and searches are slower because it has to check all lines. So moving on to a set associative mapping. Set associative mapping is the middle ground. So the cache is divided into sets, and each block maps to a specific set. But inside that set, it can go into any line. So we describe this as k-way set associative. So, for example, two-way means two lines per set. This approach balances performance and cost, which is why it's the most common choice in modern systems. Okay, so now let's move on to memory address breakdown in mapping. So the memory addresses are divided differently depending on the mapping technique. So if we talk about direct mapping technique, the address is divided into tag, cache line index, and byte offset. Then we talk about full associative mapping technique. The address is divided into tag, and byte offset. And in set associative, the address is divided into tag, set index, and then byte offset. So if we realize the tag runs through the mapping techniques, so we see that it's always important. And it's important because it confirms that the right block from main memory is in the cache. So now let's see replacement policies and then valid bit. So when the cache is full, we need a replacement policy to decide which block to remove. So in the direct mapping, it automatically replaces the block in its fixed line. In associative and set associative mapping, it uses smarter methods like least recently used or even random replacement. Or it also uses first in, first out. So the valid bit tells us if the data in a cache line is valid. So if it's zero, the data is considered empty or outdated. So now let's look at the summary table, which summarizes the mapping techniques. Okay, so now direct mapping is simple, fast, and low cost, but the disadvantage is that it has high conflict misses. In full associative, it's flexible. It has high hit rate, but the disadvantage or the cons is that it's costly and slower searches. And in set associative, it's balanced in cost, performance, and complexities. So in summary or in conclusion, we've seen that direct mapping works best for simple cost-sensitive systems. Full associative mapping technique suits small high-performance caches where misses are costly. And then set associative mapping technique is the most popular in modern CPUs because it balances speed and cost. So mastering these techniques is very essential for designing efficient cache systems and boosting computer performance. Thank you for listening.